Hi everyone. Today I'm going to share my research insights on convolutional neural networks post-compression evaluation with explainable AI. Little bit about me. I am Recep Erol, a PhD candidate at the University of Arkansas at Little Rock Computer and Information Sciences PhD program. In my PhD, I work on energy efficient deep learning and computer vision algorithms and its applications. I am also a co-founder and CTO of Smyrna AI. We provide training and education to individuals and companies and consultant services, technical consultant services to startups and companies. The contact information is listed here. You can reach out to me for inquiries, feedback, and recommendations. The agenda for today is as follows. The initial topic I would like to discuss is the importance of model compression, especially if you have multiple devices that you need to deploy your model to each of them. Next, I would like to discuss why confusion matrix is not enough on model evaluation and what kind of evaluation technique is needed for both original trained model and its compressed version. In the next set of slides, I would like to mention about the experiment setup with dataset, algorithm, and tech stack I used on implementing the experiments. I will complete the presentation with the very interesting results, then close the presentation with the conclusions. In my PhD research, I am looking to the problem of energy efficient deep learning, specifically computer vision algorithms and their applications. And I did exhaustive number of experiments from data pre-processing to model training, then its inference to model deployment, doing all these steps with different hardwares, different libraries and frameworks, and different programming languages. This study is about the evaluation of deep learning model compression and how the compressed model decision-making process has changed, or if changed, after compression. In this study, I wanted to show typical decision process of model training, compression, and deployment for companies who has different hardwares to deploy the same model. It's not necessary to have different hardwares for this guideline. You can only have one of the hardwares of edge devices that you can still do the same process for your model. Let's think of a scenario. You have multiple hardwares and you want to have the same product on all these devices. The first thing that you might do is hire multiple ML engineers and use the same data set and different size of algorithms. Train the algorithms until the point of you get satisfactory accuracy and deploy these ready-to-use models on these devices. Then think of, you need to require a lot of training resource, including hardware, GPU power, human power, and money. Also, it's very difficult to keep the same standard for all these models because different algorithms have different characteristics. Then it becomes near impossible to maintain all these models together. Another approach for the same scenario, instead of hiring multiple ML engineers, you can have neural architecture research setup with an ML engineer, and for different hardware, you can set up 4 different neural architecture research for all these hardwares, then let it train. Any guess for how long does it take to get satisfactory enough results for all these models? Couple weeks, months, maybe years. I think it's 2 positive guesses. As a result, instead of doing all these things that I have mentioned so far, why don't we train if we have enough data to start from scratch or fine-tune the one of the available large models, then compress it gradually to be able to fit to these hardwares. Therefore, we are going to have only one model with different versions of compressed model. In this case, we save human power, training resources, time, and money. However, it's still not the ideal world. Let's look at the situation of what happens after the model compression. These results are from the experiments I did for this paper. We see that the accuracy drops from 98 to 92. Okay, but where did this 6% go? Which class was affected the most? The status is still blind for us, and we can't make any logical explanation for this situation. Let me walk you through the experiment process and how I ended up in this result. The data set for the experiment of this setup, I selected animal faces high-quality image dataset. Since this dataset is originally set for style transfer, I wanted to use it for this study. The dataset has 3 classes and 15,000 images. Additionally, I used more than 100 images for testing purpose outside the input dataset. For the simplicity and popularity of the study, I decided to use ResNet50 algorithm. For the tech stack of the project, I used TensorFlow Deep Learning Library and Python API. Also, for the pre-trained weights, I used TensorFlow's ModelZoo ResNet50 ImageNet weights for fine-tuning the input dataset. For the deep learning compression algorithm, I used TensorFlow's ready-to-use network pruning algorithm. For the attention map, I use GradCam. Because GradCam is class-specific, meaning it can produce a separate visualization for every class present in the image. Couple other reasons why I chose GradCam for this purpose is that we know that attention maps are used to understand the model's decision-making process, and they give us an idea about where algorithm looks on the input image while making a decision. Although I got 98% accuracy and 97% advanced score out of the fine-tuning training process, there is no sign of overfitting or underfitting on the training process. After I applied the compression algorithm, the accuracy and advanced score dropped to 92%. So the question here is, where did this 6% accuracy go? Which class preserved the most of their knowledge? To be able to understand the compression process better, I have a couple of results to share with you. Our findings revealed that the models exhibited similar attention maps despite different decision outcomes, which may have negative implications for real-world applications. In the first example, we see that original and prune models gave correct predictions, which is expected. But the original model has a slightly higher accuracy. The attention maps for both models indicate that they focused on the same region, which is the face and mane. That is also expected. In this example, these images are from the external test dataset. It's interesting that it's interesting that the face is a cat face, but attention map focuses on the wrong area, which is the face and the fake mane. We observed that in the dataset images. Algorithm focused on the cat's mouth. These findings suggest that incorrect decisions may be hierarchically transferred to the pruned model. In these images, the models focused on the same area as in the other images, as in the previous images, mane and the face, but predicted completely wrong classes. And the pruned model has lower accuracy. This indicates a generalization issue, where information was preserved in both positive and negative ways. I would like to address a couple things in this slide. So we see that these images, original one and the pruned one, these images are from the test data set. And in the first one, it detected as dog class. And also in the pruned one, it's also detected as dog. And in the next image, they also classified as dog. And in the pruned one, it's the dog one. So this is a really crucial issue we need to address here. So the information is hierarchically transferred from original model to pruned model. Okay, conclusion. One of the purposes of this study was building a guideline for industry professionals. In case they need to make a decision about computer vision and deep learning pipeline for training and inference. Post-training evaluation, especially using explainable AI methods, can take longer than the training process itself. Why? But why, at the end, you're going to get benefit from out of it? While GradCam does add an additional layer of complexity to the evaluation process, it is a valuable tool for post-training and post-compression evaluation. Relying solely on confusion matrix results can be misleading, as demonstrated by the GradCam results presented in this study. By providing a more detailed understanding of the model's decision process, GradCam can help to identify potential weaknesses and areas for improvement, ultimately leading to better performing and more robust models. Also, this study provides a way to save energy, money, time, and engineering powers. Thank you for listening to my presentation. I hope you get benefit from it. Please let me know if you have any questions. Thank you.